Good, good. Channel your collisions and let the pressure build. Let the gas flow through you. That's right, today we're talking about kinetic molecular theory. Hit the theme.
Ain't nothing but a chem thing, baby. Two flipped out teachers going crazy. Lancaster is a district that pays me. Unbreakable, so please don't try to break this. But back to the lecture at hand.
Hello and welcome to another episode of SchuFu coming at ya. I'm your host Fu, and with me as always is Shu.
Shu know it.
So Shu, in the last episode we talked about gases and we talked about how pressure, temperature, and volume can all affect a gas in the combined gas law.
And today we're going to introduce the concept of an ideal gas and also introduce a new equation called the ideal gas law. So let's get started. Kinetic-Molecular Theory, or KMT, a lesson from the phases of matter unit. Let's actually break down these two words, kinetic-molecular. Kinetic has to do with motion, molecular has to do with molecules. So KMT has to do with the motion of molecules, just like what we see in the animation to the left. Okay, we're going to begin with the 5 assumptions of KMT and a couple of side notes. One is the purpose of these assumptions is to create a model for visualizing a gas. The second side note is we want to make sure that you memorize all 5 of these. This is more than just an FYI. These are things that you really need to know and understand about a gas. Number 1, gases consist of a large number of molecules in continuous straight line motion.
So to break down the first one, we want to say that gases have particles that are separated, they're moving in constant straight line motion. Now, that is kind of intuitive. We don't want to say that these gases are kind of curving around each other. Again, this is just kind of building this model for how gases behave, right? So they might collide off container walls, they might collide with each other, but they stay in straight lines, as you can kind of see in the diagram there in the box.
Number 2, energy is transferred by molecules during collisions, but the average kinetic energy stays the same. This is called an elastic collision.
In number 2, we do talk about energy being transferred from molecule to molecule. I guess what really illustrates this best, if you've ever seen a Newton's cradle, where you pull one of the balls up, you let it go, and it transfers its energy to the further outside marble, and then that goes up, and it keeps going back and forth. Now, if you've ever seen these work, it does seem like they go for a while, but eventually it does come to a rest because energy has been transferred, and then it also has been a little bit lost to the system with every collision. So that could be in the form of friction, and that gets lost as heat to the atmosphere, but energy is lost there. So what I want you to do is think of Newton's cradle. That never ends. It just keeps going back and forth because no energy is ever lost. And that's kind of what number 2 is saying here.
Number 3, at a given temperature, the molecules of all gases have the same average kinetic energy.
Number 3, at a given temperature, the molecules of all gases, that's the important part here, have the same average kinetic energy. Now, an example could be of a gas, hydrogen, which is just H2, which has a formula mass of 2 grams per mole, or we can have carbon dioxide gas, which has a formula mass of 44 grams per mole. They have different masses, but if they're both at, say, 273 Kelvin, they both have the exact same average kinetic energy regardless of their size.
Continuing on with number 4, the actual volume of the molecules is insignificant when compared to the total volume of the container. In other words, we can assume that the actual spheres in the gas phase have no volume.
So to break down 4 a little further here, if we take a look at the image above, we've got a container that has a gas. Those blue dots represent the gas. And we have this white space inside the container too. That can be thought of as the overall volume of the container. Now, if I was to ask you what takes up more volume inside that container, the blue dots all added up together or all of the white space, you'd tell me the white space because it's a lot more than the dots themselves. So because of that fact, because there's so much more space between the particles, we say the particles themselves have no volume.
Finally, number 5, gas molecules have no attractions for each other.
Now, in number 5, the particles having no attractions, well, we know from previous units that all matter, all atoms, all particles, all molecules, they do have attractive forces, intermolecular forces. We've talked about those. But because particles of a gas are separated and they're individual and they're far apart, that we say that attraction is negligible, which basically means it's so small, it's insignificant. So we just say that it's no attraction. Ideal behavior. Let's tie this all into real gases. If all 5 conditions exist, we have an ideal gas. Now, an ideal gas is a model which works only for an imaginary gas, but makes our calculations work perfectly. So how is a real gas different from an ideal gas? Well, looking back at those assumptions, the actual spheres of gases do have molecular volume, and the molecules do have attractions with each other.
All right, so let's take a look at some pictures. We talked earlier about how through the 5 assumptions of KMT that we would have a gas where the volume was so small of the actual particles that it would be insignificant compared to the container volume. So if you look at the left, we have an ideal gas, particles so small, really insignificant compared to the overall container volume. Now over on the right, we have a real gas. Now this is a pretty big exaggeration, but a real gas, we do see that the atoms, molecules, whatever the particles are, do have their own molecular volume. Now, the molecular volume could be large enough that it's actually taking up a significant amount of space and actually taking away from the volume of the overall container. I like to use an analogy of a classroom. So if we have a classroom and it's completely empty, we could find the volume of that room by measuring a bunch of measurements and calculating the volume of that room. Now, if we start putting furniture in and then students sitting at their desks, you're actually taking volume away from that original calculated volume. You're taking up space because you're occupying space that somebody else cannot occupy. Therefore, you're taking volume away from the room. And this is like a real gas because the molecular volume is actually taking up space that's taking away from the volume of the overall container. So we've talked already about how in an ideal gas, there are no intermolecular attractions. We make that assumption and it sort of makes everything work perfectly. But real gases could have a wide variety of intermolecular attractions. And we could have weak ones like London dispersion, but we could have stronger ones like dipole-dipole attractions. Now, these varying attractions actually do affect the behavior of a gas. If we take a look at our picture here, we have an atom that's about to collide with the container walls and exert pressure. But we see for this real gas that there are other atoms that are interacting with it. These are representing with those double arrows intermolecular attraction. So as it's coming towards the container wall, we actually see that there's attractions that are going to sort of hold it back. So those extra interactions with those other atoms affect the behavior of the gas and the collisions and in turn the pressure.
Let's discuss this idea of most ideal. So gases can behave most like ideal gases when we maximize the overall container volume with a low pressure and minimize the effect of the attractions with high temperature. Now, it's important to take away that low pressure is important here and high temperature. So on any question you might get on a test or an exam, gases behave most like ideal gases at low pressure and high temperature.
What?
Gases behave most like ideal gases at low pressure and high temperature.
Okay!
So why low pressure? Well, a low pressure implies that the gas molecules are very spread out, maybe at a very high volume. Now, what this helps out with is that the molecular volume is not as significant compared to the container volume because it's a much larger container. So, for example, if we go back to my analogy with the student sitting in the classroom and I said, hey class, we're going on a field trip, let's go to the field house, and we all go down to the field house. We didn't change our volumes as we went down to the field house. It's exactly the same. But now relative to this huge area, our volume isn't as significant as it was in the classroom. So again, we're not actually changing the molecular volume, but we're changing the effects of that molecular volume because the container is so large, there's much less of an effect. And why high temperature? Well, high temperature gives our particles more energy. They're moving faster, and that allows those molecules to actually overcome, if not break those attractions completely and collide with the container walls, collide with each other as they would if there were no intermolecular forces. Okay, next we're going to talk about the ideal gas equation, also known as the ideal gas law. This is found on table T of your reference table, specifically in the honors section. PV equals nRT. Sometimes I like to just say Puvner, it's a lot faster. Where P is the pressure in ATM, V is the volume in liters, N N is the moles. R is a constant called the gas constant. Its value is always 0.08206 liters times atmospheres divided by moles times Kelvin. Oh, that's so long to say. I'm just going to say latum over mole for short. And T is the temperature in Kelvin. Now, keeping units the same every time is important due to the units of the constant. And a little hint, use the units of the constant to remind you which units to use for the other variables. In other words, we're locked into these units. We're allowed to kind of use different units with the combined gas law, but we're locked into these units because of the units of the gas constant.
All right, we're going to take a look at the two equations we've learned so far in this unit side by side. On the left, we have P1V1 over T1 equals P2V2 over T2. That is the combined gas law equation. On the right, we have PV equals nRT, Puvnert, or the ideal gas law. The combined gas law equation pertains to the problems in which the conditions of a gas are changed. So you have a before and an after. The ideal gas equation pertains to existing conditions of gas that are unchanged.
Let's continue with some tips on using the ideal gas equation. Pressure needs to be in ATM, so if it's in kPa, convert it. And if you look at the example, we have 226 kPa given. We multiply by 1 atmosphere over 101.3 kPa because those both represent standard pressure. Our kPa units cancel out, we're left with ATM. We get 2.23 ATM. Volume needs to be in liters, so if it's in milliliters, convert it. And in our example, we have 555 milliliters. We multiply by 1 liter over 10 to the third, or 1,000 milliliters. Again, that goes back to the first unit of the year. You get 0.555 liters.
Some more tips. You may not be given moles, so you may have to convert from grams using the molar mass. So for example, if we have 5.66 grams of H2, we want to convert those into moles, so we're going to use a conversion factor of 1 mole of H2 over the formula mass of H2 being 2.02 grams, and that's going to give us 2.80 moles of H2. You may have to solve for moles even though you are asked to find the grams or molecules. You will have to convert for moles at the end. So if you solve for moles and you get 0.873 moles, and they want molecules, you're going to have to use Avogadro's number.
Hey, I just met you, and this is crazy, but here's my number, so call me maybe.
You're going to have to use Avogadro's number in your conversion factor. So you're going to multiply times 6.02 times 10 to the 23rd molecules and divide that by 1 mole, and you will get 5.26 times 10 to the 23rd molecules.
A few more tips. R will always be given to you on your reference tables, but make sure you always write the units out. Temperature must always be in Kelvin.
Temperature is always in Kelvin!
What?
Temperature is always in Kelvin!
Okay!
All right, let's do an example of the ideal gas equation. You ready, Fu?
I am.
All right, let's get started. It says if 2.50 grams of oxygen gas are present at 135 degrees Celsius and 2,500 milliliters, what is the pressure of the gas? All right, we're gonna do this FSA. What formula is gonna apply here? We're gonna use the combined gas law or the ideal gas equation?
Well, I don't see before and after conditions, like it's changed, so this is lending itself nicely to the ideal gas law.
Good, and what is that formula?
That's on my reference table, so PV equals nRT, or Puvnert.
Very good. Now, sometimes it helps to keep us very organized, to list the variables off to the side. We may have to do some conversions as well, so that's a good place to do them. We'll kind of go in order variable by variable, trying to find that variable in the question.
Okay.
All right, so let's start with P. P is pressure. Are we given a pressure in this question?
We are not, but we are actually asked for pressure. What is the pressure? So that's what we're solving for.
That's what we're solving for.
Okay.
And again, we can circle that variable in the actual formula.
Good.
So we're reminded of that. All right, so what's the volume given in the problem?
All right, the
Look at
volume units are milliliters here. So 2,500 milliliters.
Good. Now we are sort of, unlike the combined gas law, limited to certain units here. In the combined gas law, you had a before and after, and as long as we were consistent, we were good. But we're kind of locked into units because of the units of the gas constant. So what unit do I actually need to be in for volume?
So it's latum over molk.
Very good,
So the
right?
L is the liters.
Good, so we want to convert milliliters to liters.
All right, so I'll do that quickly. So 2,500 milliliters. That was way too long. times, let's see, my milliliters on the bottom, liters on top.
Good.
1 liter is 10 to the third milliliters. So that ends up giving me 2.500 liters.
All right, looks good. So we can
Okay.
write that up for V now.
Okay, so 2.500 liters.
All right,
Okay.
continuing on with N. N is the moles. Are we given moles in here?
No, nowhere.
No, okay. But it's not what we're solving for, so there must be something else that relates to moles.
Well, the only thing I haven't underlined or circled yet are grams and degrees Celsius, and I'm obviously not changing degrees Celsius, so
Okay.
I know I can change grams into moles. Yet again, another gram to mole conversion, right?
Yeah,
All right, so 2.50 grams of, it's oxygen. Oxygen I know is diatomic, O2.
good.
So I'm going to multiply that times a conversion factor, which is its formula mass for going from grams to moles. So grams of O2 on the bottom, moles O2 on top. 1 mole is 16 and 16 is 32.
Good, using the periodic table, we look up those atomic masses. That is our molar mass that we
Alright,
use. So we're dividing here
I
off your calculator.
get 0.07812 moles.
Good, and let's put that where N is, so we got it in the right spot.
0.07812 moles.
All right, so R is our gas constant. Where can we find that?
Right off the table T.
All right, very good.
That's
It's gonna be the same thing every time.
0.8206.
There's that latum
Latum.
over molk.
Molk. Like that.
All right, and finally, we've got temperature. What temperature is given in the problem?
135 degrees Celsius.
And what unit do we need to be in for temperature?
Kelvin.
Yeah, so always want Kelvin. So what do we have to do to convert it?
Add 273. And I'm going to get 408.
Looks good. So there's a lot of prep work we had to do just to make sure we had the right numbers in the right spot and with the right units. But now it should be easy sailing here because we just have to substitute those numbers in.
Okay, so let's do our substitution part. Pressure I'm solving for, so I'll leave that as P. Volume is 2.500 liters. That's going to be equal to the moles of 0.07812 moles times the gas constant. Man, this is a lot of stuff.
Sorry, we're running out of room.
0.08206, and that's platinum over molk.
One more value to fit.
I'm going to put that just down here. Remember to multiply that, and it's the temperature, right?
Yep.
So 408 Kelvin. 408 K.
All right, so we're gonna multiply everything on the right. We're gonna divide by the 2.5 to get our final answer as a pressure. Let's talk about Sig Figs. Let's go back to the original numbers.
Okay, so I've got a measurement of grams there of 3 Sig Figs. Here I have a measurement of 3 Sig Figs. Here I've got 2.
That one's only 2. There's no decimal there, right?
So least amount of Sig Figs is 2, so 2 Sig Figs. Doing all of this math, I end up getting to 2 Sig Figs 1.0.
Let's talk about units. Yeah, it's pressure, so it's atmospheres. Why don't you show the unit cancellation real quick with the gas constant, just so we see what that would look like.
Okay, so moles here divided by moles cancels out. Same thing with Kelvin divided by Kelvin. Now I divide both sides by liters. Liters cancels out. That just leaves my gas constant with atmosphere, so that works out nice.
Perfect. You try. How many molecules of an ideal gas are contained in 3.0 liters at STP? Now again, you want to use FSA. I highly recommend you list all your variables off to the left. And you might notice there's a few tricks here. STP, remember what that means. And it looks like we're solving for molecules as our final unit in your answer.
Well, that's going to do it for today's episode on KMT.
It's been emotional.
Today's episode is brought to you by...
Put your pet to work with Todd Lawson's Pet Expressions, the pet painting kit. 15 tail grip brushes, 8 paw pad boots, 1 washable palette, and 4 paper canvases.
So Shu, in the last video we talked an awful lot about gases. We pulled focus to gases, and yeah, That's what we did. Let's try it again.
True story, bro.
They're always moving in the same. Why am I reading it again? All 5 conditions exist. We have an. Just read it, Fu. Ideal.
Nope.
Nope.
Nope. What this helps does.
What this helps does.
This helps. What
That's how
this helps do.
That's how the gas does it.
And allow them to move around and collide as they should. No. So why high temperature? Well, particles at a why high temperature? Particles at a high temperature have a lot more energy and they're moving a lot more faster. More faster? I didn't even realize that was incorrect for a second.
A lot much more faster.
Not no, much. No. Nope, wrong hand motion.
Oh, this is not it. This is okay. This is not it. T1 equals P2 over P2 over V2. Ha.
But we never off, always on till the break of dawn. SCIENCE in the hall they call S-Wing. You know we never wear a tie like my homies, boys to men. It's so hard to say goodbye.
Like this, that, and this, and it's like that, and like this, and like that, and it's like this.
You're going in low power mode.
Plug and chill to the next episode.